Hey, great hands. So now we're going to go over lesson 5 of unit 5. So trigonometric identities, we're just moving on to lesson 5 now. So learning objective, obviously, is pretty simple. We're going to be learning how to prove trigonometric identities using the Pythagorean identity, the quotient identity, and then the reciprocal identities as well. So first of all, let's start with the main definition. What's an identity? So an identity is an equation, and be careful with this. It's not just an equation that is true for all values of a variable. So really important that you understand this. It's an identity is an equation, but doesn't mean that all equations are identities, right? It doesn't go the other way around. So an identity is an equation where it's true for all values of a variable. So for example, you know that when we analyze a circle and using Pythagorean theorem, we do know that there is definitely a special identity that we are aware of. We know that x squared plus y squared equals r squared. And you actually might remember this because I know some of you had mentioned that you didn't cover equations of a circle before in grade 10, but I'm sure that you learned about the distance formula. So if you remember, the distance formula was a change in x squared plus the change in y squared is equal to the distance squared, or you might have called it something else, L squared, or whatever it might be. It's basically the same idea, right? We're just saying that we're finding out what the x coordinate is, we square it, and again, an x coordinate on the circle, and then we take the y coordinate of a circle, we square it, and then that gives us the radius squared. Um, so that's the first identity that you probably learned about in high school, at least, right? You probably learned about other identities as well. Just so you're clear, it's not just any equation. It has to actually work for all values. So for example, this is an equation, x squared plus 4 is equal to 13. But if you look really carefully here, x squared plus 4 is equal to 13. That is true, but it's only true for -3 and +3. So for these values, if we sub in 3 here, I get 3 squared plus 4. That's definitely equal to 13. Same with -3. If I square it and then I add 4, I definitely get 13. So it works for both these values. But in order for it to be an identity, it has to be true for all values of x. So that's a really important definition that you understand there. So trig identities specifically are identities that involve trig ratios, hence the name, and they must be true for all values of the variable. Identities can either result from a definition, so they either come directly from a definition, or we can get them by observing the relationship between different trig ratios, right? So essentially what all these identities are stemming from are from other identities that we accept to be true from either definition, or we can see the relationship between the trig ratios. So here's a table showing you the most important trig ratios that we're going to work with in grade 11. Um, Keep in mind that basically if you know these, then the rest of it is actually just a matter of deriving the different definitions, right? We're just deriving different identities, but really this is the cornerstone of what we're doing, and you need to remember these, okay? And I would even say, and a lot of times students will tell me, well, can I just keep it in my notes? Sure, you can have a table with all the identities, but I'll be honest with you, if you actually know these by heart, it makes the work a lot easier, because the toughest part about identities is that you have to be able to not just look at them and be like, oh yeah, I know that one, but you be able to recognize them within more complex expressions. That's when it gets really tricky. So the better you know them, the faster you'll be able to identify them and then use them to manipulate your expression to whatever you need it to be. Um, so keep in mind, I'm just going to briefly explain these. The reciprocal identities, I mean, they are identities, but I sometimes always tell people that this is more a definition. We really actually know this just from definition, right? We know that cosecant theta is 1 over sine theta. It's just a reciprocal of sine theta. Secant theta is simply just the reciprocal of cosecant it was the reciprocal of cosine. And the cotangent is simply the reciprocal of tangent. So these three right here, I always tell people, these look scary, but they're not. This is actually just a definition. It's actually not too complicated. These two sets of identities right here, the quotient identities and the Pythagorean identities, these are extremely important, extremely important. And these do not necessarily stem from a definition. We actually have to do a little bit of work to derive them. Now, I don't know if I will necessarily give you a question on the test where I ask you to derive these, because this is a little bit more standard. But again, I recommend that you understand it well, because I think I've mentioned this a couple of times. A lot of times in math, students focus on just memorizing, and that gets really complicated. I don't recommend you do that. Really try to understand it, and that in that way, it makes I wouldn't say even memorizing, but recognizing it a lot easier, right? Eventually, you won't even have to necessarily put a lot of effort into memorizing it. You'll just kind of recognize it because you'll understand the concepts, right? If you understand these concepts, it's actually not that difficult. So again, quotient identities and the Pythagorean identities, we actually have to derive them. So we're going to look at how to derive these two sets of identities that we have. So let's start with the quotient identity. So let's prove that tan theta is equal to sine theta over cos theta. So that's the first identity we're looking at there. Again, I mentioned this already. These three right here are all by definition. So, I mean, I have them on that list, but really you don't, I mean, there's nothing to memorize. You should hopefully already know that, cosecant, secant, and cotangent are the reciprocals of sine, cosine, and tangent, respectively. It's the quotient identities and the Pythagorean identities that we have to do a little bit more work. Okay, so let's look at the first one. Tangent theta is equal to sine theta over cos theta. So how do we prove that that's true? Well, we know on the left-hand side that tan theta is what we want to show is equal to sine theta over cos theta. And normally when we prove identities, and this is the first example, we label it by side. So we call the left side LS and the right side RS. So we want to show that tangent theta is equal to sine theta over cos theta for all values, right? Not just one particular value. So what we want to do in this case is we want to make sine theta equal to y over r, which we are allowed to do because remember we learned that identity. It's not actually, it's an identity, but really it's more just a definition. We learned that in a Cartesian plane, if we have an angle like this, so this is my principal angle there. My y-coordinate is right across, and my radius is the hypotenuse. So that means that my sine of theta, ratio of theta is y over r. And then we know for this angle right here that cos theta is equal to x over r. And again, this is just a definition that we talked about before. So knowing these two identities, how can we use this to prove that that's equal to that sine theta over cos theta is equal to tan? Well, I know that sine theta over cos theta will be written as y over r divided by x over r. So we're having a fraction divided by another fraction. So how do you divide fractions? Well, we know we divide fractions by multiplying by the reciprocal. So what I'm going to do is I'm simply going to take my numerator, y over r, and I'm going to multiply by the reciprocal of the fraction in the denominator. So I'm going to multiply by r over x. And when I do that, the r's cancel out. And then I end up with y over x. And notice that y over x, if you recall the definition, y over x is actually equal to tan theta. So by definition, we already know that that's equal to tan theta. So that is why tan theta is equal to sine theta over cos theta. So again, now that we proved this, you don't have to prove this over and over again. So I want to make it clear that you can take that as an assumption now, right? This is always going to be true. So if I know that tan theta is equal to sine theta over cos theta, how can I figure out the second identity there? So my second identity is that that we're given is that cotangent theta is equal to cos theta over sine theta. So how can I prove this? Well, we know that cos theta is going to be equal to, as I mentioned, is going to be equal to x over r, and sine theta is going to be equal to y over r. So we can actually solve it the exact same way. We can set it up in the exact same way that we did here. We can divide the two fractions there, or two ratios, and then we would find that this is equal to x over y, which is obviously going to be the reciprocal of tangent. Or the other way that you could do this is simply realize that that cotangent is the reciprocal of tangent. This is probably the easiest way to do it. Or cos theta, well, the cotangent is simply the reciprocal, right? So we switch the numerator and the denominator there. So that means that the cotangent of theta is equal to cos theta over sine theta. And again, it's worth simply memorizing that tan theta is equal to sine theta over cos theta, as a lot of different identities are going to come from that. And I wouldn't say memorizing it. I would say almost just you're going to see it enough times that it's going to become second nature to you, right? And again, tangent is simply the reciprocal. All we're doing is simply switching the numerator and the denominator around. So pretty simple there. All right, let's look at the Pythagorean identity. So how do we prove that sine squared theta plus cosquared theta is equal to 1. Well, again, this is what we're trying to do, is prove that the left-hand side is equal to the right-hand side, which is equal to 1. And we're going to talk about some strategies here, but essentially we want to focus on the more complex side there first, the left-hand side. And we know that cos theta is equal to x over r. So if sine theta is equal to y over r and cos theta is equal to x over r, that means that sine squared theta plus cos squared theta is simply going to be equal to y over r squared plus x over r squared. And again, I just want to be clear on this. I know some of you had asked about this before. When you see sine squared theta, what that really means is sine theta squared, right? It's the exact same expression. So what we're saying here is we're taking the ratio for sine theta, y over r, and we're squaring it. And we're taking the ratio. If we do that, we end up getting y squared over r squared. So we squared the numerator and denominator. So apply the exponent to the numerator and denominator. Apply the exponent to the numerator and denominator. Then we get y squared plus, y squared over r squared plus x squared over r squared. And then, of course, if I'm adding fractions, I need to make sure they have the same denominator. They do, which makes it easy. So because they have the same denominator, I add y squared plus x squared. And we actually end up with an identity, another identity that we need to make use of. Remember the first identity I mentioned to you already? I mentioned in a circle, or using Pythagorean theorem, we know that x squared plus y squared equals r squared, right? And the reason for that, again, if we draw a little unit circle here, if I have my point x and y, this is my y coordinate right here, this is my x coordinate right here, and this is my radius, I know that x squared plus y squared equals r squared, right? Because they create a right triangle together. So I can actually use the fact that x squared, y squared plus x squared is equal to r squared. Notice that the only difference is that the order switched, but it's the same answer there. So I can replace y squared plus x squared with r squared. For r squared, the r squared divided by r squared is equal to 1, which means that sine squared plus cos squared is equal to 1. So going back to our Pythagorean identities, I'm just going to prove the other two derivations of the Pythagorean identity. So how do we derive the following identities? So we found the first one. So the first one was that sine squared theta plus cos squared theta is equal to 1. How do we prove the other two? The other two are actually not that bad. The other two are just derivations of it. So what we notice in this case is that if I take my first expression there, let's focus on the first one, proving that 1 plus tan squared theta is equal to secant squared theta. And then we'll focus on the second one after, okay? So in the first identity there, we want to start with the fact that obviously sine squared theta plus cos squared theta is equal to 1. And again, that this is true, right? We just proved it, right? We just did it. If we didn't prove that, then obviously you couldn't use that. But we can use it because we just proved this true. So what I'm going to do is I'm going to divide the whole entire equation by cos squared theta, which again might seem a little bit silly to you that I might do that, but let's do it. So we're going to take sine squared theta here. So I'm going to write this over here at the top. Plus cos squared theta is equal to 1. I'm going to divide both of them by cos squared theta. Sorry, I'm going to divide the whole entire equation by cos squared theta. And again, why am I allowed to do this? Well, because as long as you're doing it to the whole entire equation, left side and the right side, then there's nothing again wrong. Nothing, you're not breaking any rules there, right? So we're dividing both sides, all parts of the equation by cos squared theta. When I do this, I end up getting tan squared theta plus 1 is equal to secant squared theta. So I'm going to explain this step by step. Sine squared theta over cos. Let's start with the basics. Remember how we said that sine theta over cos theta is equal to tangent? Well, if I multiply by sine theta over cos theta again, so if I multiply by itself, it should be pretty obvious, I hope, that you will notice that you have tan theta times tan theta, and that ends up giving me tan theta squared. So that's how I ended up with tan theta squared. What about cos squared theta over cos squared theta? How did I know that's 1? Well, obviously, any value divided by itself is 1. Cos squared theta. How did I know that that was 1 over, so how did I know that was secant squared theta? Again, it's not exactly the same as what we had in the table that was given to us at the beginning, but I hope you realize that 1 over cos theta is simply secant, right? Because this is the reciprocal. And so the only difference in this case is that this was squared. So if that's squared, then what do you think you have to do here? You simply square it. And so I rewrite this as secant squared theta. So I'm hoping that kind of makes sense so far. So now that I have that identity, I look up and I just check, have I proved the order is slightly off, but just put the 1 in front and it doesn't make a difference at all, right? Because when you add, you can switch the order around. So I have 1 plus tan squared theta is equal to secant squared theta. And that's my first identity. For my second identity, for the second one here, 1 plus cotangent theta is equal to cosecant theta. So what we're going to do is we're going to start off the exact same way. The only difference is that we're going to divide, instead of dividing sine squared theta plus cos squared theta is equal to 1, by cos squared theta. We're going to divide it by sine squared theta. And again, this is extremely hard to say. I find just a lot of these questions are even just hard to even mention, right? They're just really long. Okay, so again, what do we notice? Sine squared theta divided by sine squared theta is equal to 1. Cos squared theta divided by sine squared theta, we already talked about this, is basically like the tangent, right? What's the only difference is that it's the reciprocal. So it's the reciprocal of tangent theta squared. So it would be cotangent theta squared, right? It's just the reciprocal of tangent theta squared. And then, of course, 1 over sine squared theta, we know that this is the reciprocal of cosecant theta squared is equal to cosecant theta squared. And that is our identity. So we prove them both. And that is, again, just showing you how we derive the Pythagorean identities. So hopefully you understand that. So now that we have proven all these main identities that we rely on, you don't have to prove them anymore, right? We already proved them. Again, I don't think, but I will give you other test questions where you have to take advantage, where so you're using these identities to prove other identities, okay? And we'll get into that. So how do you prove identities? So if you want to prove an identity, what you're really doing is trying to prove that the left side equals the right side. So to do this, so any identity in the table, you assume that we already know that. And you're going to be using algebraic skills to also simplify. So these are helpful little tips. They're not rules, okay? So I don't need to come back to me and say, Mr. Pineda, you said to do this, and I followed it and I didn't get it right. The hard thing with identities, and I'll be honest with you, identities are tricky. Like even for myself, sometimes I have identities that I find extremely complex. So the hard thing with this is that there is literally no set rule. No one has like a set of rules that they're like, to follow this and you'll always get the answer. You won't always get the answer, right? Sometimes it's a little more complicated. But these are just some tips. Start with the most complicated side first, okay? And then what you really want to do, instead of working with both sides at the same time, I would recommend starting with one side at a time. So start with the left-hand side, or start with the or simplify as much as you can as you go along, and then just kept checking to see if the left side equals the right side. So it's a bit of a strategy game as you go along. If you want to check, like, am I on the right track? Well, keep looking at your identity and check, does the left side equal the right side, right? The closer they get to looking like each other, the closer you are to your answer. It's kind of like a Rubik's Cube, right? You almost have to like stop and check, like, are you close to your end game or not? And if you're not, then your helpful tip is to rewrite trig ratios as x, y, and r if that helps. It doesn't always work, but sometimes it helps. Try to rewrite the expressions using the same trig ratio. That's really important. You don't want to have, sine, cosine, tangent, cotangent. You don't have all 4 trig ratios or all 6 of them. Sometimes you may have to find a common denominator so that you can add or subtract rational expressions. So remember, Unit 2, we learned about rational expressions. That's going to come back, right? You want to make sure that you know how to add and subtract rational expressions. And if all else fails, if you tried it and it doesn't work, then try a different method. So let's prove these identities. So cos theta times tan theta is equal to sine theta. And then let's do sine theta, cos theta times tan theta is equal to 1 minus cos squared theta. And secant theta is equal to tan theta times cosecant theta. Let's start with the first. I will start with the left-hand side because it seems more complicated. So if it's more complicated, then there's more to simplify. So then it's easier to get it to look like the other one, like the other side. So first thing I realized is that I can rewrite tan theta as sine over cos, right? And that's probably going to be helpful to us so that I can then eliminate the tan theta and just have sine theta and cos theta. So when I do that, when I rewrite tan theta as sine over cos, this cancels out and I end up with sine theta on its own. And of course, sine theta is equal to sine theta. There you go. Pretty simple. Obviously, we already proved that. We already proved that this left-hand side is equal to the right-hand side. So sometimes what we can do for notation, and a lot of people will do this as well, you actually can start off by saying the left-hand side is equal to cos theta, tan theta, right? And then you're going to prove all this work. And then eventually you're going to say that this is equal to the right side, right? Which is sine theta. I didn't do it in this case. I think a lot of these examples, I was just trying to be mindful of space, but on a test, I would definitely start it off that way. I would say left side is equal to this. You're going to prove you're going to do all the work to simplify it, and then you're going to prove eventually that it's equal to sine theta, and then you say the left side. Next example. This one's a bit more complicated, but I would again start with the left-hand side because even though this does look complicated, but I think that there's more to simplify here. So again, my first strategy, rewrite tan theta as sine theta over cos theta. I just feel like whenever you have sine and cos and then you have a tangent in there, try to write tangent as sine over cos, right? And when you do this, you actually notice that the cos theta and this cos sine theta times sine theta, and sine theta times sine theta is sine squared theta. And now you look at this, and unfortunately, you're still not done yet. You want it to look like the right-hand side. So this is where you have to strategize. So let's think here. I want sine squared theta to look like 1 minus cos squared theta. Well, what is one of the identities I know? I know that sine squared theta, this is the Pythagorean identity, plus cos squared theta is equal to 1. So what I can do here is I can simply move the cos squared theta to the other side so that I can get the sine squared theta on its own. And when I do that, when I get the sine squared theta on its own, I realize that sine squared theta is equal to 1 minus cos squared theta. So that means that sine squared theta can be written as 1 minus cos squared theta. And lo and behold, that's equal to the right-hand side. So because it's equal to the right-hand side, and you can just put right underneath, this is equal to the right-hand side, you know that the identities are equal to each other. So because the left-hand side equals the right-hand side, it's an identity that's proven true. So hopefully that makes sense. Let's look at the next one's part C. So again, always look for the more complicated side. In this case, we switch around our game. It's actually the right-hand side cosecant. So you might want to remember, okay, cosecant isn't that the reciprocal of 1 over sine? Oops. Isn't that the reciprocal of 1 over sine? Sorry, let me just move this around. Hopefully you do recognize that. That's a reciprocal of, sorry, I meant to say the reciprocal of sine theta. So we're going to write it as 1 over sine theta. So hopefully you recognize that, that's a reciprocal there. And again, the reason that's going to be helpful to us is because we can then take our we're going to take our right hand side tan theta times cosecant theta. We're going to rewrite that as tan theta times 1 over sine theta. Now, what else can I do? Well, I can rewrite tan theta as sine theta over cos theta. And again, why is that going to help us? Well, by doing that, the sine theta cancels out, and then I end up with 1 over cosine with 1 over cosine theta, and that obviously leaves me with 1 over cos theta like this. And I recognize that this is the reciprocal. Cosine theta is the reciprocal secant theta. So if I have 1 over cosine theta, then that's equal to secant theta. And notice that secant theta is equal to the left-hand side. So we can see here clearly that the left-hand side is equal to the right-hand side. So we have proven that this identity is true. So here's a more complicated one. Prove that cosecant theta is over cosine theta. Okay, let's go through this one step by step here. Sorry, I just want to check one small thing. Yes, we still have a couple more. Okay, so what I'm going to do in this case is I'm going to start off with the right-hand side. And the reason I would start with the right-hand side is because it doesn't look more complicated, but it actually is more complicated because you're adding the two different expressions. And again, these don't seem like, it doesn't seem very, like I said, it doesn't seem that complicated, but right now this is kind of complicated because trig ratios here. So what I'm going to do first is I'm going to rewrite cotangent theta as the reciprocal of 1 over tangent. Sorry, I'm going to rewrite it as the reciprocal of tangent theta, right? So that means that I have so far tangent theta is sine theta over cos theta. And of course, if tangent theta is equal to sine theta over cos theta, the cotangent theta is going to be equal to cos theta over sine theta. And how do I know that? These are just reciprocals of each other, right? So if tan theta is equal to sine theta over cos theta, that's an identity. The cotangent theta will be cos theta over sine theta. And I apologize. I feel like this is even hard to say, so I can imagine how this sounds. It just sounds crazy. Just bear with me, okay? So in this case, we want to find a common denominator. So to find a common denominator, this goes back to grade 9, grade 10. You want to find an equivalent fraction. So let's find the common denominator first. Well, a common denominator in this case is going to be, means that I want to rewrite both these fractions so that I can get a common denominator of cos theta times sine theta. So what do I have to multiply the numerator and the denominator by to get to a denominator of cos theta times sine theta? Well, I need to multiply this by sine theta. So I multiply this by sine theta, and then I end up getting sine theta squared. And now I'm going to do the exact same thing for the other fraction, sorry, for the other rational function there, rational expression there. So I have cos theta over sine theta. I want a common denominator of cos theta sine theta. So I'm going to multiply this by cos theta. So hopefully everyone's understanding that so far. I just need a common denominator. And then once I find the common denominator, I'm finding the equivalent fractions. So now I have cos squared theta over cos theta times sine theta. That's my equivalent fraction there. So now that I have the equivalent fractions, I'm just going to add them up. So I'm going to add sine squared theta over cos theta times sine theta plus cos squared theta over cos theta times sine theta. And when I do that, like I said, I end up getting sine squared theta over cos squared theta times sine theta plus cos squared theta over sine squared theta times cos squared cosine theta. Sorry, and I'm sure I'm making mistakes as I say this. One of those where it is extremely hard to say, but I would just follow with what I've written here. So now that I have a common denominator, obviously I'm allowed to add the two fractions, and I just have to add the numerators. So now I have sine squared theta plus cos squared theta over cos theta times sine theta. And now I realize that sine squared theta over cos theta, is that an identity? Yes, it is. I know that sine squared theta plus cos squared theta is equal to 1. So I can actually rewrite the numerator as 1. And I write that as 1 over cos theta times sine theta, right? So all I did was use the Pythagorean identity to make this equal to 1 there, right? Simplify this as much as I can, but unfortunately, I look up here and I realize it's still not equal. But is it starting to look similar? Well, there is some similarities. Cos theta is in both in the denominator in both cases. This has a sine theta, this does not. But I noticed that this has cosecant theta. And you might recognize that cosecant theta is the same as 1 over sine theta, right? So what I'm going to do here is I'm actually going to take this fraction here, and I'm going to split this fraction up into 2 parts. I'm going to rewrite it like this. 1 over cos theta, and then the other fraction that I'm going to multiply by is 1 over sine squared theta. And so what I notice here is that 1 over sine theta is actually the same as equal to the cosecant theta. So then I'm going to rewrite 1 over sine theta as cosecant theta, and now I have 1 over cosine theta times cosecant theta is equal to, and then of course now I just multiply the two expressions here. So I multiply the numerators first, and again this automatically has an imaginary denominator of 1. So I multiply 1 times cosecant theta, and I multiply cosine theta times 1 theta, and that is my and now I notice that this is equal to the left hand side. So obviously the left hand side is equal to the right hand side. And again, I haven't really showed this expression at the very end, but whenever you do identities, you should always specify that the left-hand side equals the right-hand side, and that's how you know it's true, okay? So hopefully that made sense so far. Let's do a couple more examples. Okay, so let's do the first one here. It gets a little, like I said, some of these get a little more complex, but hopefully you're able to work through them all. And again, I just want to make sure that you're kind of following so far. So in the first one there, we have cos squared theta. Oops, I'll just read it to you. Cos squared theta is over 1 plus sine theta is equal to 1 minus sine x, right? And I keep saying theta, and actually it's x in this case. In this case, to be honest with you, it's a little bit tricky, but I would say the left-hand side is still more complicated, right? So what I'm going to do now is I'm actually going to try to rewrite the left-hand side a little bit differently. But one thing I noticed is that this has a cosine, this has a sine theta, but the right-hand side has a sine theta as well. So it seems like sine theta seems to be the common trig ratio that we have there. So what I'm going to do is I'm actually going to rewrite cos squared theta, so sine x squared, as 1 minus sine squared x, right? So I'm going to use my Pythagorean identity to simply rewrite this as 1 minus sine squared x. And the reason I do that is because then I can have all my expressions in terms of sine. It's going to be easier for me to work with this. Now, this does not look that simple, and you're probably wondering, what do I do next? I'm hoping that you realize that this is actually just a matter of factoring, right? I look at the numerator at the top and think from before when we did difference of squares. So remember how we talked about difference of squares? So if I give you something like 1 minus x squared, and then I ask you to factor that out, well, you notice that this is a perfect square, right? So I can take the square root of 1, and I get 1, and I can take the square root of x squared, and I end up getting x. So because they're both perfect squares, I can actually just take the square root of each of them, and then I put my answers in here. In the bracket, sorry, I put the answers in the brackets here, but I switch the sign. And again, this is just a little shortcut we use. So we write 1 plus x, 1 minus x, or you could use sum and product factor, right? But in this case, to be honest with you, the easiest thing to do is just use the fact that this is a difference of squares. This is a perfect square, and this is a perfect square. So that means that I can actually rewrite 1 minus sine squared x as 1 plus x times 1 minus x, right? It's actually sine squared x. So believe it or not, it's the same idea here. What we're going to do in this case is simply take the square root of 1, that gives us 1. Then you take the square root of sine squared theta, sine squared x, and then I end up getting sine x. And what I'm going to do is simply put the square roots in the brackets. So we have 1 plus sine x, and then it's going to be 1 plus sine x multiplied by 1 minus sine x. And I simply write that expression as a factored expression there. And I did this for a reason. I realized that 1 plus sine x, nice about this is that I can actually factor this out like that, right? So this makes it a little bit easier for us to simplify this expression. So we factor out the numerator denominator, and then we cancel out our common factor. And when we do that, we end up with 1 minus sine x. And notice that that is equal to the right-hand side. So because the left-hand side is equal to the right-hand side, the identity is definitely true. Okay, we know it's definitely true there. Let's look at the second example. So we have the cotangent theta is equal to 1 plus cotangent theta over 1 plus tangent, 1 plus tan theta. So what do we do first? Well, what I'm going to do is start with the the right-hand side, because again, it's more complicated. We have a fraction there. And then I realize is that the cotangent theta can actually be rewritten as cos theta over sine theta. And obviously tan theta can be written as sine theta over cos theta. And where am I getting this from? That's the quotient identity, right? If you're wondering where I'm getting that from, that's just an identity that we were given. So why do I do that? Well, what I want to eventually do is try to see if I can simplify the division of these two expressions here, right? So I want to try to reduce this rational expression here. It's a bit complicated, but let's just start with what I know. Well, denominator. So what I'm going to do in this case, I'm going to do it step by step. I need a common denominator, and the common denominator here is sine theta. And we're actually kind of lucky. Since it's 1, it's pretty simple. We need to multiply the numerator and the denominator of 1 by sine theta. So I can get a common denominator sine theta. And then by doing this, I can then add my numerator and denominator. I can add my numerators once I have a common denominator there of sine theta. And I'm going to do the same thing here. So I'm going to rewrite 1 as cos theta over cos theta. And again, we know that we're allowed to do that because that's equal to 1. And then I'm going to be adding sine theta over cos theta. And again, all I'm doing is finding a common denominator here. So now that I have a common denominator, again, what am I allowed to do? I'm allowed to add the numerators there, right? So what I'm going to do in the top fraction there, so in my top rational expression, sine theta over sine theta plus cos theta over sine theta, I'm simply going to add the numerators. That ends up giving me sine theta plus cos theta. And this is all divided by sine theta. And then, of course, this whole entire expression here, let me erase this so I can actually, I feel like sometimes it gets messy here. This whole entire expression right here is equal to this, just so everyone's clear on that. This is equal to that. Now, that whole entire rational expression is then going to be divided by this whole entire rational expression right here. So first thing, sine theta over sine theta plus cos theta over sine theta, that becomes sine theta plus cos theta over sine theta. And then, of course, in the denominator, cos theta over cos theta plus sine theta over cos theta. Geez, this is really hard to even say. Hopefully you guys are keeping up with this. So now we have sine theta plus cos theta over sine theta, which I can divide by this rational expression here. And remember, when I divide by rational expression, and we learned this in Unit 2, that is equivalent to multiplying by the reciprocal. So what I'm going to do is simply find the reciprocal of this and then multiply. So I rewrite this as sine theta plus cos theta over sine theta times cos theta in the numerator divided by cos theta plus sine theta. And what I realize now is that cos theta plus sine theta, it appears in the numerator in the first fraction and the denominator in the second fraction. So that means I can cancel them out. So this cancels out. And then I end up with cos theta over sine theta. And what's cos theta over sine theta? Well, cos theta over sine theta, we know is equal to the cotangent of theta. And that is equal to the left-hand side. So that means that the right-hand side is equal to the left-hand side. So we have proven our identity there. These are tricky, guys, okay? And if you're looking at this and you're like, holy smokes, I know I went through this a little bit faster, but I'm hoping that this kind of makes sense so far. This takes practice, okay? I'm telling you right now, identities, I always found it one of the hardest parts of, one of the hardest lessons, actually, because there's not really one set way to do it. It's kind of a puzzle, right? You have to try different strategies. And if it doesn't work the way that you tried it, you can try something else, right? Let's do the last one here. Okay, the last one is complicated. Let's just theta minus 1 over sine squared theta plus 3 cos theta minus 3 is equal to cos squared theta plus cos theta over negative sine squared theta. Okay, that's even hard to say. Let's start with the left-hand side. So again, the left-hand side is extremely complicated. So I would start with that first. So what do I know so far? Well, first thing, the fact that the fact that you have a sine squared theta, cos squared theta, there's a mix of sine and cos to go to your left-hand side and rewrite everything as the cos squared, as in terms of cosine theta. You could obviously try a different way, but I think it's easier to rewrite sine squared as cos squared. Rewrite the sine ratios as cosine ratios. The reason for that is because in this case, when I have cosine theta, it's not that easy for me to switch this. I can't really switch that into a sine theta, right? It's not very possible for me to do that. But if I have sine squared theta or a cos squared theta or sine squared theta expression respectively, right? I can switch them around. So it's easier to switch around the sine squared theta and the cos squared theta into a different trig ratio, right? So what I would do is I would actually switch the sine squared theta into 1 minus cos squared theta. And how do we know this, by the way? This is coming from the Pythagorean Identities. we know that sine squared theta plus cos squared theta is equal to 1. So if I simply subtract off the cos squared theta, I end up with 1 minus cos squared theta, right? So this is easier to work with, right? So I rewrote the sine squared theta as 1 minus cos squared theta. And then this ends up giving me this new expression that doesn't look like it's that doesn't look like it's easier, but it will actually become a little bit easier, I promise you. So first thing, I have 1 minus cos squared theta plus 2 cos theta. And then here I have minus cos squared theta plus 3 cos theta. And then I have a negative 3. And of course, the negative 3 is added with the 1. And this ends up giving me minus 2 or negative 2. So now I have this new expression, which again, doesn't look that easy. But I want to think to myself, what could I possibly do here? Well, at this point, you want to consider factoring. Remember how I told you that was one of your little tips? Don't forget about factoring. I know a lot of you are, I know it gets messy and I know it's a little bit complicated, but I mentioned this from day one. You really want to be good with factoring, right? Because this is a tool that even now, we're not even talking about quadratics, but we're still going to be using this trick. So again, this is actually something I brought up before of introducing a dummy variable. A dummy variable basically is just representing it with a different variable. We can treat cos theta as if it were just one big variable by itself. I know it's actually not a variable because technically the variable is theta, but I'm going to treat cosine theta, if I treat cosine theta as a variable itself, I can then factor it out like I normally would using sum of product or using common factoring, right? So in the first scenario here, what I'm going to do, again, I'm just, like I said, treat cosine theta as if it was one variable. So that means that my numerator here is going to be rewritten as negative cosine theta squared. Think of it this way, right? So this is kind of like an imaginary x plus 2. And I'm putting this in brackets on purpose so that we can treat it as if it were one big variable. So again, treat the cosine theta as if it were one big variable x, if you want to think of it that way. I know it's not actually equal to x, but let's just treat it as if it were one big variable. And we're going to do the same to the numerator. We're going to treat the cosine theta as if it were one big variable. So it's negative cosine squared theta plus 3 cosine squared theta minus 2. And again, I'm going to treat this as if it were x squared. I'm going to treat this as if it were x. And I'm going to treat this just as a constant. So really, this is like, it's almost like I have rewritten this expression as x squared plus 2x, right? So again, if this expression, I know it's not the same, but if the numerator right here was x squared plus 2x, let's figure out what we would do if it was x squared plus 2x. Let's just say that that was the expression. I know that's not the case, but what if it was the expression? Well, it's actually pretty easy to factor. We hopefully know how to do this. You common factor out the negative x, and I specifically could take out the negative there, so you don't have to worry about the negative signs. And then we end up with x minus 2. So pretty simple to do. It is if it's a quadratic. I know it's not a quadratic, but I'm going to treat it as if it's one. We have negative x squared plus 3x minus 2. Okay, again, I would common factor out the negative x. So then you can factor using sum product, the easy trinomial method. So I want to think to myself, what adds up to negative 3 but multiplies to give me 2? Well, what adds up to negative 3 and multiplies to give me 2? That would be negative 1 and negative 2. So it's going to be negative outside the bracket times x minus 1 multiplied by x minus 2. This is my factored expression. So I already factored it out. So what's the only difference here? Instead of having an x, I'm not going to write an x. I'm going to replace the x with cosine theta. So every time I see x, I'm going to rewrite this as cosine theta. So I go back up to my factored expression. And you see every time I see x, I'm going to rewrite that as cosine theta. I'm going to rewrite this as cosine theta. And same with this. I'm going to rewrite this as cosine theta. I'm going to rewrite this as cosine theta, like that. So that means that I end up getting this factored expression, negative 1. And again, the negative 1 is coming from the fact that I factored out a negative number there, times cosine theta multiplied by cosine theta minus 2. And then in the denominator, I have negative, and I have a negative sign outside, cosine theta minus 3 cosine theta plus 2. But I actually went one step further, I already factored it out. So I have negative cosine theta minus 1 and times cosine theta minus 2 in the denominator. And in the numerator, I have negative cosine theta times cosine theta minus 2. Now what do I notice? Do I notice anything special here? Yes, I do. I notice that now that I factor my expression, now I can factor it out. Now I can factor out the common factor here, cosine theta minus 2, because it comes up in the numerator denominator, so I factor it out. And now in my next expression here, this longer expression that I had really simplifies to something a little bit easier now. It's negative 1 cosine theta over negative cosine theta minus 1. Now, I look back up here, And unfortunately, I did a lot of work and I still don't have that expression. So this is a little bit frustrating. And this happens sometimes. You do all this work, you think you're working so hard, you think you're close, and unfortunately, it still doesn't look the way it's supposed to look. That's still not what I wanted it to be. So what could I try? Well, I'm not gonna lie to you, it gets frustrating. So what you need to do now is think to yourself, well, I still don't have it looking like the right-hand side. But if you look at the right-hand side, you might want to think of what you can try to do to simplify it further or work backwards. So it may be helpful, that's what I meant to say, it may be helpful to simplify the right-hand side separately. So if we look at the right-hand side here, we have cos squared theta plus cos theta is equal to negative sine squared theta. So I might notice that sine squared theta, negative sine squared theta, I can actually rewrite that as negative 1 minus cos squared theta. And again, we kind of already did that in the first step. So I'm just simply rewriting it a little bit more. So by rewriting it, it might give us a little bit of a hint as to what I can do to make the left side equal the right side. So I go back up here and I think to myself, okay, going back to the right-hand side now. So now it's kind of strange that I went to the right-hand side. And again, this isn't always a strategy we try, but sometimes we try, well, as soon as I simplified the left-hand side, the right-hand side. I mean, I did the left-hand side as much as I could. Now let's go back to the right-hand side. Well, I noticed on the right-hand side that I have, sorry, going back here, I think I made a mistake. Yeah, so we're gonna work backwards but we're still gonna continue on with the left hand. Sorry, I thought it was the right hand side. It's the left hand side. Sorry, made a mistake there. So I'm gonna go back to my left hand side, and I know that if I simply multiply the left hand side by the conjugate, and again, I don't know if you've learned about this yet, but basically we noticed that this essentially cos squared theta minus 1. If I multiply it by cos squared theta plus 1, it will actually cancel out, and this really looks like the expression that will give us the difference of squares, right? So what we're doing here is we're essentially multiplying the numerator denominator by cos squared theta plus 1 over cos squared theta plus 1, right? And we're doing this so that we can eventually get this to what we have on the right-hand side. So when we do this, we end up getting cos squared theta times cos squared theta, which is cos squared theta squared. And then cos squared theta plus times 1 is cos squared theta. And then in the denominator, we have cos squared theta minus 1 times cos squared theta plus 1. And again, I didn't show the work here, but I'm hoping that you can see how I got this. I'll just briefly show you this. I multiply out, I get cos squared theta. And then I have cos squared theta times 1, that's positive cos squared theta, minus cos squared theta. And then negative 1 times positive 1 is minus 1. And then this cancels out and I end up with cos squared theta minus 1. So notice that now this expression looks more familiar to us. The only difference is that the right hand side had a sine theta instead of a sine squared theta instead of a cos squared theta minus 1. And the only difference really is that I had it kind of rewritten a little bit. So I had cos squared theta minus 1. And if you recall, we know that sine squared theta is equal to 1 minus cos squared theta. So what's the only difference here? The only difference is that the order is changed in subtraction. So whenever we discussed this, that when you subtract numbers and then you switch the order, the answer switches signs, right? We switch signs in the difference, right? So for example, 5 minus 3, we know is equal to 2. But if I do 3 minus 5, we know that's equal to negative 2. So notice I get the same answer, just different signs. Well, that's what I'm doing here, right? I notice that cos squared theta minus 1 is the same as 1 minus cos squared theta, except that the sign is different. So I put a negative sign in front. And then we notice that that is equal to the right-hand side. And now we are fully done. So we notice that cos squared theta minus 1 is equal to negative sine squared theta, cos squared theta minus 1 on one side. So this is a really tough one. Don't stress about this. I don't think I'll put something like this on the test. You may have something where you have to factor. I feel like the factoring part is reasonable, but the last part of the question I think is a little bit difficult, and I don't think I'll put in something like that. So a couple little caveats here, okay? As I mentioned already, you can't just conclude that an equation is an identity if the left side equals the right side. I know that we do this when we do equations, but that's to check if it's true for one value and then prove that it's true forever for all values, right? So for example, sine squared theta plus cos squared theta, you could say it's true by simply subbing in 45. So if I sub in 45 into this equation here, you're going to see that the sine of 45 degrees and the cosine of 45 degrees are equal. So you could look at that and say, oh, then it must be true for all of them. And then you check for 225 and it's also true. And then you would even think, wow, then it must be true for all theta. That's not the case. And you can't prove an identity by simply subbing in numbers. That's not how it works. It's not true by just finding one example for which it doesn't work. So if you're able to find one example for which it doesn't work, then you can prove that the identity is wrong. But proving that something is wrong is easier than proving that something is right. Proving that something is wrong just requires you to be wrong once. It's like the vertical line test, right? You just have to fail once. But proving that something is true is harder because then you have to prove that it's true for all values. Does that hopefully make sense? Hopefully it's clear. So square theta plus is equal to cosquare theta. That's definitely not an identity because if I, for example, sub in 0, if I let theta equal 0, you're going to see here that sine theta, sine of 0 degrees is 0. We actually learned about that. And the cosine of 0 degrees is 1. So notice that they're not actually equal to each other, right? So we have 0 and 1, and obviously they're not equal to each other. So because it's not true for all values, then we definitely know that it's not true. We know it's not going to be an identity. So it is easy to prove that something is not true, but it's hard to prove that it's actually true for all values. So final reminder here, proving identities, as you can see here, is tricky. There's not really one strategy that works for everything. So you have to try different strategies, and it's going to require some work. It's going to require a trial and error, and that's frustrating. I get it, but you just have to keep trying, okay? Practice makes perfect. And having said that, I really do mean this. Please do not spend hours and hours and hours on one question. I've seen some. Honestly, if you can't figure it out, just take a break, come back to it later, right? Sometimes just taking a break from it and coming back to it later will help you a lot more. And don't stress, right? Take it one step at a time. Just see what you can do, okay? Don't do your best and don't let one question consume you completely. Alrighty, there's the homework. And again, as I mentioned, but keep your sanity as well, okay? All right, best of luck.